Hi everyone. So as I promised, it's a Sunday evening and I'm going to take this video to respond to a couple of the questions that people had. So the first question I wanted to address was a notational one. Uh, and it's an important thing to clarify just because the notation looks similar. And what the question was the difference between this and this. So they might look similar, but there's in fact an important difference. So this here, this is the expectation value of x, right? And we talk about the expectation value, right, in the following way. It's the average value that you would expect to get if you were to measure the position uh, in an ensemble or in a large number of identically prepared systems. And that's going to be given by, right, sandwiching x in between my wave functions, or alternately, I can think about, right, it's x times the probability density, right? So this is sort of the average value, whereas this delta x, right, is the uncertainty. A little bit of grid there. And right, and this right tells me the spread in my x values, and I can think of this in the following way, right? I can think of this either as the sort of as the average of the deviation from the mean value, so sort of the average of, right, x minus x, expectation value quantity squared. Um, Actually, I need to square root that. Um, Equals, whoops. Or I think of this, right, in terms of that theorem we've been using where delta x equals the uh, square root of the expectation value of x squared minus the expectation value of x, the quantity squared. So the picture that might help to think about it is the following. So suppose I had some wave function, and let's just assume for sake of argument that this is some sort of nice sort of, that's sort of some sort of nice bell curve shaped wave function like that. Pretend I drew it uh, somewhat more symmetrically. And let's just imagine that we have this sort of symmetric peak right at x naught. Now, from the shape of this distribution, you would probably intuit that, right, the average value of the position that you would measure would be x naught. And so here, right, the expectation value of x would be x naught, whereas the uncertainty in x would be a measure of how wide this was. So something like, this isn't really a good picture, but like something like that would be the uncertainty in x. So that's an important point to distinguish. Um, there's another question that came up was uh, what's special about solutions to the time-independent Schrodinger equation? So this is actually something I thought was worth addressing in the main video I made for today's class, which I shot before I got this question. So I do want to refer you there for a more detailed discussion. But let me just highlight sort of two things. that I think are particularly important. That solutions to the time-independent Schrodinger equation are energy eigenfunctions, right? So they are wave functions that have a definite energy, number one. And number two, they time evolve in a really specific way, right? And so the full wave function, right, is the stationary state psi n times e to the minus I e nt over h bar, and right, and what this means and why they're called stationary states, remember, is that the probability density associated with this time-dependent wave function is constant. But as we saw, you can understand how arbitrary states time evolve by breaking an arbitrary wave function into a sum of stationary states and then time evolving each term in that sum according to this. So the third question that that I wanted to address, that it's a very good question, is so what does it mean for two wave functions to be orthogonal? Orthogonality mean? And so I think the question is not so much a, well, what does it mean mathematically, but what sort of physically does it mean for two wave functions to be orthogonal? Now, there's a couple of ways one can try to think about this. It is, I think, an inherently sort of mathematical concept, but I think this is um, where sort of analogy might help, and maybe it helps for me at least to think about a counterexample, so a case where two things aren't orthogonal. And so I'm going to go back to thinking in 3D space. So let me draw I'll only work in 2D to make it easier to draw. Let me draw a 2D plane here. And let's think about vectors in 2D for a second. And suppose instead of what we did the other day, and we talked about writing arbitrary vectors in terms of like I hat and j hat and k hat, suppose I wanted to write everything in terms of the following two unit vectors instead. So suppose let me choose one unit vector. So let me just have I hat let me have I hat defined in the usual way, pointing along the x-axis. But let's suppose that I wanted to use another unit vector instead of j hat that, instead of pointing perpendicular to I hat, let me just call this u hat for unit vector. Suppose it pointed at a 45-degree angle or something like that, right? Such that I hat and u hat were not orthogonal. The consequence of this really is that doing vector math becomes much more of a pain in the neck working with non-orthogonal basis vectors than it has to be. So, right, for example, right, so suppose that I had some like vector that pointed that pointed this let's say I had a vector that pointed diagonally, right, like this, right? It points along the u hat direction for sure, but it also has a component along the I hat direction, right? Because there is still some sort of horizontal component here, right? Any vector pointing in the u hat direction sort of has some I hatness to it. And the same is true here, right? Any horizontal vector has a non-zero u component, right? And then now, right, adding vectors becomes trickier too, right? Because if I wanted to, right, if I want to just add some horizontal vector, well now, right, it's going to affect both the u and the I hat components of this vector, right? So I think, without going into um, to much more detail, right, vector math gets more complicated, right? It becomes hard to write arbitrary vectors in sort of a in a way that where the components are physically meaningful in the sense that the components are physically independent, right? Where because right in a normal coordinate system, x and I hat and j hat are perpendicular. We can manipulate sort of those independently without worrying about something we do to one component affecting what we do to another component. When we think about sort of the implications for quantum mechanics, I think it's really quite similar to this, right? So I would say that so in QM, sort of orthogonality underpins lots of things. And this might actually be where watching the bonus video for class, I guess it was class 28, might actually give some insight, because there I went through in detail exactly how orthogonality is a critical step in a couple of the results we've used. So for instance, right, um, so orthogonality turns out to be critical if you want to find those expansion coefficients C sub n, right, in the expansion of a arbitrary wave function in terms of energy eigenfunctions, right? It turns out to be showing, that the sum of those coefficients modulus squared gives you 1, right? And this is the whole reason, right, why, or part of the reason why we can interpret, right, the modulus squared of those coefficients as a probability, right, for measuring energy E sub n. Right? Because if this were not true, then right, you can't have a probability where the total sum of all possibilities doesn't add up to 1. So right, so in some sense, like the theory falls apart, or at least becomes much clunkier if you don't have orthogonality. And the other thing the other thing, right, the other result I talked about um, is, right, I talked about the expectation value of the Hamiltonian, and how one can calculate that turns out to also rely uh, on orthogonality. Now, there is one thing that I want to say, and which is that, well, if orthogonality is nice and helps us, right, how do I get it? It turns out you can, if I have two like non-orthogonal vectors, so like if I had like this u hat and I hat, like in this example, um, then I can always construct a pair of orthogonal vectors, and it turns out the same thing is true for wave functions. Right? So I can always construct orthogonal basis if needed. And if you take linear algebra, the answer to this, you might be familiar, is what's called the Gram-Schmidt, I can't, Schmidt procedure. So you're always guaranteed to be able to construct an orthogonal basis. So you might as well just assume that your basis is orthogonal and make your life simpler. I don't know if that completely sort of answers the sort of physical sense of like what does it mean for two wave functions to be orthogonal, but I think to me, right, the this the ability to sort of do any useful calculations in quantum mechanics becomes really a lot harder if you don't have orthogonal wave functions. And maybe for me, the best way to think about it is to think about, well, what does it mean for what are the mathematical consequences of having two vectors be perpendicular? So I hope that this video has helped to answer some of the questions that people have had. I'm happy to continue discussing these points with you offline if you want to discuss them further. And again, if anybody has any questions going forward, just let me know, and I'm happy to do this again.